Now then let's look at the SRAM, right? Let me quickly review again. On the top right, there is a SRAM cell, and it has 6 transistors, right? On the right, this is an inverter, and you see that the output go to the left. On the left is the inverter, the output go to the right, so I draw it in this way, right? And then on the right, I have another inverter, so this is Q2, Q4, right? This is Q1, Q3, right? And that's it, because that is enough to store your information, right? Because it's a regenerative. Remember, we have been saying regenerative, although this is a very trivial thing for you, but that is the critical thing you need to think about when people propose a new technology to you. Everything looks so nice, but it might not be regenerative. Then the noise will be a problem. You might need to refresh it, right? And we call that, we do have 2 transistors. Do you remember what do we call these 2 transistors?
Bistable, I think.
I say again?
Bistable configuration.
Bistable, but bistable is talking about this and this 2 coupling inverter, right? Is bistable, either at 1 or 0. But what is the name of this transistor in SRAM? Do you remember the particular name I said?
SS transistor.
SS transistor, yes. Right? Why we want to remember? Because that's how people talk about it. And then it also tell you what it is for, because it let you to access the SRAM. When the word line is at 0, they are cut off, then you cannot access that transistor. Just like the door is closed, the box is closed. You don't know what is stored inside, right? In order to open it, I need to turn on the word line. So it becomes a wire, right? Of course, it's not a wire we're going to analyze, right? But it's just like shorter, right? From the 0th order approximation. And this is called word line. So this line is connected to many SRAM cells. So when it's turned on, then the whole row will be turned on. The whole row can get access, but the other row, they cannot. At the same time, we have 2 columns, which called bit 9 and bit 9 bar, right? So this, I did not crop it well. So it is BL, bit 9, okay? So bit 9 is let us to do something, including reading, writing, okay? Both of them, okay? So now I want to show you how we read it, right? I kind of talked about that last time. When we talk about read it, right? Don't get, when you see this type of problem, the first thing, just cool down. Think about what problem you want to solve, right? For reading, the best, I hope that you can memorize the algorithm, right? If not, it's not a big deal. I don't think, I cannot say, probably it won't test you this type of stuff in the exam, right? Because I hope that when you need it, just Google, you find it. Wikipedia will tell you. So to do it, what it first does is charge the bit 9 and bit 9 bar to VDD. Charge it to VDD. That is the first thing. Okay. And then we turn on the word 9 to VDD. Okay. So you can see that under this situation, I have the high voltage connected to the SS transistor, also high voltage connected to Q6. And at the same time, this is on, so they are shorted, right? Now, let's say then to analyze, we need to make an example, right? So we just assume that, for example, this is at 1. For example, this is at 1, store 1. If this is 1, we know this is 0, because it's just like what you just said. It's a bistable one, right? If this is 1, after the inverter, this is 0, right? So if this is 0, what does it mean? Q4 is on, right? Because 0 is applied to the gate of Q2. Q2 has to be off, and 1 is applied to the gate of Q3. Q3 is off. And then, of course, Q1 is connected to 1, so it's VDD, Q4 is grounded. So the circuit is really simplified. And then our question is, how do we read it? Okay, to read it is what? We read it to see the difference of V at bit 9 and V at bit 9 bar, right? You can imagine, I put this at VDD, this at VDD. If this one is also VDD, is also 1. No current will flow, so this one is still at VDD. But for this 9, because the other cell is at 0, it's going to discharge my line, right? It's going to discharge it, and then it changed from VDD to VDD minus delta. This is talking about the voltage of bit line bar, right? And then you have a sense amplifier. You measure the difference of these two lines. And then you see that bit line bar is lower, then you know that the cell stores 0. On the other hand, if bit line is lower, for example, if this is 0, this will go down, this will stay at 1. Then you know that it's store 1. That is how you read the SRAM cell. Is that okay? Any questions? Now, if no question, then what? Then easy, right? But then you need to be careful, because if this one is pulled to too low, for example, eventually it pulls so that this point is no longer 0. Sorry, not too low. If the current is too large, this point is no longer 0, right? Because you have current going through here. It can go up higher, right? So, when reading, right? When reading, the voltage, I call this X, right? V at X will go from 0 to delta V, right? Just because of the voltage divider effect, right? Because if this is VDD and I have current going through here, then this cannot be 0, because if there's 0, I won't have current. So it will be delta V, right? So we need to make sure delta V is smaller than the VTH of which one? Of Q2. Why? Because this node is this node. This node is connected to Q2. Just now we say that Q2 is off because it was at 0. If you pull this voltage up to be larger than VTH of Q2, then this will turn on. Once it turns on, this is no longer 1. You have a potential to go to below 1, go to smaller than Vm. And then the content will flip. Once it flips, this becomes 0, this will become 1. And then when you're reading, although you read the correct data, you know this stores 0, but you flip the content to 1 already. So you destroy the content. That is not what we want. Okay? Is this clear? So for that, I can draw a circuit, right? I know that this potential divider is Q5, and Q5 is at gate is at VDD just because it is connected to the word line. And this is Vx. And it is connected to Q1. Q1 is grounded. Again, this is VDD. And both are NMOS. This is not PMOS. And this is bit 9 bar, also VDD. Okay? So I need to solve the equation, right, to find out what is Vx. Can you tell me, right, which is equal to delta V? What is the mode of operation of Q5? Anyone? We have 3, right? We have 4 maybe. Cut off, linear, saturation due to velocity saturation, saturation due to channel length modulation, right? Actually, you cannot distinguish the last one, but at least can you tell me which one of them, which one is that? Is it cut off, linear, or saturation for Q5? Right, so this is like, I can just not teaching this slide and then ask you to solve in the final exam because you learned that already, or I did not teach you, I did not say this is SRAM, just a circuit, right? And tell me what equation you should put. And you did that in midterm 1. See me, not this question, but right, you should learn that already. What is the mode of operation of Q5? Now you might got confused, but at least you should ask me some question, right? How do you, what do you need to know in order to determine the mode of operation of Q5? How about let's start with Q1. what is the mode of operation of Q1? Do you have enough information to know the mode of operation of Q1? Is it cut off, linear, or saturation? Or how about let's tell me, is it on or off for Q1? Is it turn on or turn off for Q1? How do we find it? We remember, how do we compare? We compare the VGS minus VT, right? Remember? I'm going to erase this, but VGS minus VT, VD set, and VDS, right? Remember? Which one is the smallest one in this case? Probably you don't know, right? But at least you will figure out. First of all, I actually hoping you to ask me the question, right? You may ask me, what is Vx? We really don't know what is Vx, but Vx is very small for a normal operation, right? Or before I destroy the content, Vx has to be small. It starts from 0, and then I start turning it on, Vx is going to go up. So Vx is very small, and it means VDS is smallest, right? For Q1. So which mode of operation is that if VDS is the smallest?
Linear.
Linear, right? So here I skip the cutoff state, but you know it is on because VDD is applied to here. So VGS minus VT is larger than 0. So this is in on state. So this is linear, right? Now, can you continue? If you say this is linear because you say Vx is very small, then what will be the operation condition for the Q5? Will it be linear?
Saturation.
Say again?
It's a saturation.
Saturation, right? This is because for the Q1, we have small VDS. This one, we have large VDS, right? Because X is small, so VDS is VDD minus some small value, okay?
So can we say Vx is a high impedance node?
Now, you need to be careful. If you say Vx, then you're talking about the voltage. So voltage has nothing called high impedance.
I mean that node.
That node, right? Where
Yeah.
are you looking into, right? You remember when you say high impedance, you need to look at different direction, right? So are you looking into here in parallel or whatever? But it has nothing to do with high impedance because by definition, right? This one is, I mean, we only talk about voltage. The voltage is very low. And it can still, the transistors can still be very conductive with low impedance, right? If you have a very small resistor, if you make the voltage across it small, you have a very small current. Actually, I don't know if I answer your question, but it is not about high impedance or low impedance because they are both on, so we can say they are low impedance. We are not talking about analog signal here, right?
Okay.
If you talk about analog, looking down is high, looking up is low, small, looking up is 1 over GM, what looking down is RO. Okay. Okay, so with this, then I can write down the equation, right? Because IQ5 has to be equal to IQ1. So what is IQ5? W on L5, mu C ox, this is for the N, right? And then multiply by VGT times, this time because it's saturation, and we assume it's velocity saturation. This is something I did not give you. VD set minus VD set squared divided by 2. Do you remember this equation? Yeah, yeah. And this one is going to be equal to W on L of number 1 mu COS, right? But this time it's VGT times VDS because it's in linear. Okay. Then of course we need to be specific. What is VGS? What is VGS here? Can someone tell me what is VGT? Sorry, what is VGT of Q5? Forgot. VGT is just VGS minus VT, right? So it's VDD minus VX minus VT, right? And what is the VGS? This is actually VGT. What is the VGT of Q1? Can someone let me know? What is VGS for Q1?
It's VDD
Just
minus
VG.
Thank you. Yeah, just VG, but VG is VDD, right? But VS is 0, so 0, but as you still have T, so minus VT. Okay, so this equation tells us that what is the Vx we can have, but maybe here I should put delta V because I say delta V is Vx. And then you rearrange the equation, you get this one, okay? Now, no worry about memorizing this equation or put in the cheat sheet, right? You don't need to do that, right? The point is that now you see that we introduce a ratio called cell ratio. It's the W1 divided by W5. Do we want it to be large or small without even looking at this equation? The problem of this question is I want to read the SRAM cell, but when I read it, I don't want to bring up Vx too high, okay? I don't want to make it 0.5 volt that has a larger than the VTH of Q5. I want to keep it as small as possible. So in order to keep it as small as possible, how should I size Q5 and Q1? Should I make Q5 much larger than Q1 or much smaller? In other words, should I make the resistance larger in Q5 or in Q1?
larger resistance in Q5, so smaller size of Q5.
So it means that you want to have a smaller. You mean you want to have a smaller W5, right?
Yes.
So you say that the larger beta is better. You want to explain to us why is that?
Because we want a smaller delta V at that node, so resistor should be high for Q5, and resistor is inversely proportional to the width.
Very good. So basically, if I call this R5, this is R1, right? You see that basically we're doing this VDD, R5, R1, and this is Vx. And Vx equal to R1 divided by R1 plus R5 times VDD, right? So that's what she's doing. She want to make R1 really small so that Vx is almost 0. When R1 is really small, then it means W1 is really large, right? So when you design your SRAM cell, if there's no other constraint, you will say that, let me just make this R1 very powerful, make it large. Okay, I want it to be large. Okay, any questions? Now, here shows what you just said, right? So I want the Q1 to be stronger than Q5. So when you lay out, you use minimal size for Q5, okay? Because you also want to save the area, right? So the one that is resistive, we make it smaller size because the W is small, okay? But so you see that when this cell ratio, again, what cell ratio? Width of R1, width of Q1 divided by Q5. If it is large, you see this delta is smaller. If you make the Q5 double the size, doubly stronger than Q1, you see that it's going to pull up the V, delta V all the way to 0.5 or 0.6. It's enough to flip the SRAM cell. But if you make it large enough, not opposite, Q1 is 2 times larger than the Q5, then you only come up a little bit, probably it is still stable. right? So in terms of stability, larger cell ratio is better, okay? Now, but this is just for the stability. You also need to think about the currents. I also want to have a larger current, although I say minimum, right? But if I size them both larger, then you have a larger current. Larger current means what? I can discharge the bit9 bar faster. Then I can have the read operation faster, right? If this is very resistive, even you don't, both are resistive, it may take 1 second to discharge. Then your SRAM is very small, right? But once you make larger, then you have the area problem. And how about the power? So now you come back to this PPAC, right? You need to find the constraint. So it's a constraint problem, okay? Any questions? If no, then let's look at the write operation. Now you see that write operation asks for different things, right? So now you have the same scenario. We say that, okay, my 1 is here. Okay, this is what was stored there, right? And I want to write it. I want to write it to another value. I want to change this to 0. And I want to change this to 1, right? Once I write it, I flip it, then I write the cell successfully. Now, this time you want to flip it, right? So let's see how we do that. So again, to write it, you cannot charge both to VDD because you really need to put the value you want to write, right? So this time I put the bit9 to 0, okay? And I put the bit9 bar to 1 because my intention is to make this 0 and then I change this to 1. In terms of configuration, it's still the same, right? This is 1, first step, and then second step, you turn it on, right? Turn it on so I can start writing it. But because it was stored, usually before the storage is at 1, so again, this is off, like what we did earlier, because this is 1. So you put this 1 to the gate, Q1 is on, Q3 is off, right? And similarly for Q2 and Q4. So this is the scenario. Now, then you will see a dilemma. How can I write this guy? If I try to write from the left side, it means that I want to make this one really high. When I'm reading, remember, I don't want this one to change much. I put VDD, right? This is VDD. I'm trying to read. When I'm writing, I also put VDD, right? So in this side, reading and writing have the same setup. So if I say that my design is so good that you are not going to flip me, then basically I'm saying that you are not able to write me by changing this one, because I already make Q5, Q1 much stronger than Q5. There's no way for you to flip me, right? VDD at most, I only go to 0.2 volt. But by changing this to 0.2 volt, these guys still have the feedback of 1. I will always stay the same number. So this time we need to look at another side, and hopefully this one can let us write it. And fortunately, it can do that. So what we are going to do is, instead of trying to make this 0 to 1, we try to make this 1 to 0. Once this one can go to 0, then due to this feedback, is going to turn off this transistor and turn on the Q3. And then we are not relying on the potential divider. We're relying on this generative feedback to flip the cell. Okay, is that clear? Now, if that is the case, right, let's draw the circuit again. Now, this is the right side, right? We try to write from there. I'm not saying that it's always right from bit9. It really depends on what is stored, right? If you store 1 and 0, then you are actually writing from here. If you try to write 0 to bit9 bar, right? But it's always that you try to flip the 1 to 0. Okay, so how do you flip the 1 to 0? You have this Q4. This is grounded. This is VDD, right? This is Q4. And this Q4 was at VDD. And then you also have this Q6, which is VDD, right? This Q6 is VDD because of the word 9, right? Word 9 equal to VDD. And here this is grounded because this is bit 9. Okay, so your goal, right, is to put VDD to 0, right? And not really 0. The goal is actually make it smaller than the VTH of Q1. Because once this is smaller than VTH of Q1, this is connected to here. Then we are going to turn off Q1. Once I turn off Q1, this one will go up. And then it will come back to do the regeneration and then help me to go to 0. So my goal is this. Right? So that's why you see that we have this this difference, right? So you want to do this, but then you ask yourself, how should I size? Here I have typo, this is Q6. Now, how should I size the transistor? Should I make Q4 stronger or Q6 stronger? If you want to write it successfully, should I have let's ask ourselves actually, instead of Q, right? Let's, again, this is a potential divider. I have R6 and R4, right? This is bit 9, this is VDD. And this is what I want to try, Vx, right? The goal is from VDD to 0. What should I do? How should I size R4 and R6 so that I can make this one to 0 easier? This is very similar to what we discussed before in right operation. Should I make R4 large or R4 small? Right? If R4 is 0, it's very small. Will you be able to make Vx to 0 if R4 is very small? No, right? Because just for potential divider, if R4 is 0, this is always VDD. There's no way for you to make it to 0, right? So we want to make R6, right, much smaller than R4, which means we want Q6 to be stronger than Q4. So that what does it mean if Q6 is stronger? We have this so-called pull-up ratio. It means I want to have small PR, right? I want Q6 to be stronger, means W6 to be wider than Q4. Any questions? Or my internet has problem? Do you hear me?
Yes, please.
Okay, good. Okay, so I see no one answer, and also no question, right? I assume you are okay, but looks very confusing, right? But not really, right? So this is just a summary. When the pull-up ratio increase, then you will be more difficult to put this 1 to 0. So you want to have small one. But it's very easy to memorize. Memorize in this way. Pull-down transistor has to be stronger than the SS transistor, and that is stronger than the pull-up transistor, right? So just go up. Maybe this is not a complete picture. Look at this. Stronger, weaker, weaker. Just go up from bottom to up. Make it smaller and smaller. Then you will satisfy the read and write operation. Okay? But you cannot make the pull down too small because it can also affect the stability of read. That is funny, right? Isn't that I say that they are decoupled? But that is just because, yeah, you make the Q5, let's say you make Q1 very strong, that is okay, but you still have delta V. And this delta V, if you make Q the pull up very weak, then it means it has a very large threshold voltage. So it's very easy for you to turn the Q4 off, right? Because if this one go to VDD, Q off is off, but it doesn't have to go to VDD minus VTH, right? It can be if it's very weak, then you can turn it is very easy to flip it. So it's not just say that I make Q1 very large, Q5 okay, and then the pull up very weak, then everything will settle, because you still need to think about the stability. They still have some coupling effect you need to consider, but you can do a lot of simulation to figure out, right? So after this class, if you have interview, if you want to memorize for the rest of your life, just memorize in this way. Bottom is, you want to break the bottom large, so it's very strong, and then go to the middle less, and then pull up is the weakest. Okay, any questions? Okay,